Hi everyone, Sherry Ann here and welcome to my chemistry hub, and today we'll be doing a CSEC past paper and this is January 2013 question 1. So let's go. So it reads, Derek performed 4 experiments to investigate how certain factors affect the rate of production of hydrogen gas when zinc metal reacts with dilute hydrochloric acid. In experiment 1, which was done at 30 degrees Celsius, he added 1 gram of granulated zinc in excess to 0.1 mole per dm cube hydrochloric acid and measured the volume of hydrogen gas liberated after 2 minutes. He then performed 3 other experiments with the following variations. In experiment 2, he varied the concentration of the acid. In experiment 3, he varied the form of zinc. And in experiment 4, the temperature. In each experiment, the gas produced was collected for the same period, 2 minutes. The data for experiments 1, 2, 3, and 4 are summarized in table 1. So essentially, he's carrying out 4 experiments and changing the condition of one. Either it changes the hydrochloric acid, the concentration of the hydrochloric acid, or the form of the zinc, or the temperature in each experiment. And then he's measuring the volume of gas liberated. Okay. And so this is the gas syringe that is used to measure the volume of gas liberated. And the first question reads, define the term rate of reaction. So rate of reaction essentially is a measured change in the concentration. So rate of reaction is a measured change in the concentration of the reactant or product with time at a stated temperature. So rate of reaction is a measured change in the concentration of the reactant or product with time at stated temperature. So those are the key terms that you want to remember when defining rate of reaction. Simple, easy, 1 mark. So the next question reads, read from the diagram in figure 1 and record in table 1 the volume of gas produced for each experiment. Experiment 1 has been done for you. So here we have, we have the table and we need to read and record the volume. So experiment 1 has been done for us, and experiment 2. So each graduation is 2, so 2 cm cube. So this will be 162, 164, 166, 168, 170, and 172. So in between, so right here would be about 171, right? Hope we're seeing that. Experiment 3. So 180, 182, 184, 186, 188. So in between, right there will be about 187 cm cube. 40 or 42, 44, 46. So 46 cm cube. So I hope that we saw that. C, write a balanced chemical equation including state symbols for the reaction between zinc metal and dilute HCl. So we have zinc, this should be easy. Area solid plus HCl, it's aqueous, right? Going to zinc chloride, that's aqueous, plus hydrogen gas. Are we balanced? No, we're not balanced because we have 2 hydrogen here with 2 there. So 2 HCl. Yes, so that's for your 2 marks. Identify the oxidizing agent in the equation, that we just did, and give a reason in terms of oxidation numbers why the agent is oxidizing. So first of all, what is an oxidizing agent? So when a substance acts as an oxidizing agent itself, so the substance itself is reduced, right? And the substance you experience, so if it's reduced, reduction is a decrease in oxidation number. So that's what we're looking for, a decrease in the oxidation number. So let's look at the zinc. So let's look at the zinc in the reactant side of the equation and the zinc chloride. So zinc, so what's the oxidation number of zinc? So any element that when it's in its free state or in its uncombined state, the oxidation number is 0. That's all we have there. So how about zinc chloride? Well, we can calculate that. So let's say X represents zinc plus the oxidation number of chlorine is -1. I mean, you'll know that in time, from doing these type of calculations. And since there's 2 of them, multiply that by 2 equal, and the sum of all the oxidation number of elements in a compound, is equal to 0. So therefore, simple transposition, we have X being equal to +2, right? Yes. So as we can see, there's an increase in the oxidation number. Let's look at the hydrogen in the HCl. So first we have HCl on the reactant side, right? And we have hydrogen gas. So what's the oxidation number of hydrogen gas? Yes, 0, you're correct. How about H in HCl? I mean, we could calculate it. So it's X, and we know plus -1 equals 0. Simple transposition, X is equal to +1. So as you can see, there's a decrease in oxidation number. So what that tells us about the HCl is that it is acting, because remember what we stated is that the oxidizing agent, the substance itself is reduced, and reduction is a decrease in oxidation number. So there's a decrease in the oxidation number, so therefore, since there is a decrease in the oxidation number of the hydrogen, HCl acts as the oxidizing. Since there's a decrease in the oxidation number of the hydrogen, HCl acts as the oxidizing agent. Yes, that's your answer for that. So the next question is calculate the maximum volume of hydrogen gas at room temperature and pressure, RTP, that would be produced when 1 gram of zinc reacts with excess dilute hydrochloric acid. So calculate the maximum volume of hydrogen gas at room temperature and pressure that would be produced when 1 gram of zinc metal reacts with excess dilute hydrochloric acid. So they gave us the RMM. So one thing when you read a question, look at everything that they give you. So they gave us the RMM of zinc. 1 mole of gas occupies 24 dm cube at RTP. So from that RMM, we can find the number of moles of zinc. So the number of moles is equal to given mass over RMM, molar mass. RMM, relative atomic mass. So then you have the given mass being what? 1 gram, right? 1 gram, that's the mass that I gave you. Divided by the REM, which is 65 grams per mole. That answer is 0.015 moles. Let's start with moles. Now what we want is the moles of gas produced. Sorry, the moles of gas produced. All right. So working with what they give us, we have to work with what they gave us to find out what we want. So they gave us the mass of zinc used and the mass and the RAM. So we need to use that to answer the question. So how can we link number of moles of, this is number of moles, zinc. How can we link that to the gas produced? The equation, right? So the equation that we produce, that we wrote in question C. So based on the equation, 1 mole of zinc, see right there, is equal to 1 mole of hydrogen gas, right? So based on equation, 1 mole of zinc is equal to 1 mole of hydrogen gas, right? So if 1 mole of zinc, think about it, if 1 mole of zinc is equal to 1 mole, it's 1 to 1, then what you just calculated here, 0.015 mole of zinc must be equal to 0.015 mole hydrogen gas. Can we appreciate that? Of course we can. It's 1 to 1. If 1 mole is equal to 1 mole of zinc is equal to 1 mole of hydrogen gas, then 0.015 mole of zinc is equal to 0.015 mole hydrogen gas. Oh, sorry. No, wrong page. Go back. Yes. So what's the next step? Remember that they gave us this? Remember this? Right? So if 1 mole of gas, is at RTP occupies 24 dm cube, what does 0.015 mole occupy? X. So based on what they gave us, 1 mole of gas occupies 24 dm cube. 1 mole of gas occupies 24 dm cube at RTP, so 0.015 mole occupies X. So basically you're cross multiplying. So X times 1. So X is equal to, and X is the maximum volume of hydrogen gas, right? X will be equal to 24 multiplied by 0.015, which is equal to what? 0.36 dm cube. And that's the maximum volume of hydrogen gas at room temperature and pressure that will be produced when 1 gram of zinc metal reacts with excess dilute hydrochloric acid. So basically, based on what they give us, kind of work our way down. So we found the number of moles of zinc produced when 1 gram, and then we related that to the number of moles of hydrogen produced, right? And then from that, we can find the maximum volume of hydrogen gas produced at room temperature. So you see the steps, right? Hope that everybody understands that. So that's how you get your 3 marks. Then it says, that's the next question, which is the final question, I think. Compare the volume of gas produced in experiment 2, 3, and 4 to the volume produced in experiment 1 and give an explanation in each case. Now, let's go back and just fill out so we have some here to work with. So remember, experiment 2 was about 171, experiment 3, 187, and experiment 4, 46. So read the question again. Compare the volume of gas produced in experiment 2, 3, and 4 to the volume produced in experiment 1 and give an explanation in each case. So let's compare experiment 1 and 2. So experiment 1 and 2, what changed? So we have the form of zinc the same, temperature the same. So what changed is the concentration of the dilute hydrochloric acid used, right? And when they change the concentration, we're seeing an increase. You can see there? An increase in the volume of gas liberated. So experiment 1, you have 0.1 mole per dm cube. And this, you have 89 cm cube. Experiment 2, you have 0.2 mole per dm cube of the hydrochloric acid used, and we're getting 171 cm cube. So that's an increase in the gas liberated. Why is that so? So they said to provide an explanation. So basically, with rate of reaction and increase, so with rate of reaction, I'm just going to shorten it like that, ROR, an increase in the concentration results in an increase in the rate of reaction. Increase in the rate of reaction. But why? Why is this so? The thing is, when you increase the concentration, you increase the number of particles per unit volume, hence increasing the frequency of collision. So when you increase concentration, this leads to an increase in the number of particles per unit volume. Number of particles per unit volume. And this leads to an increase in the frequency of collision. And this leads to an increase in rate of reaction. So that's how you'd explain your answer, right? So let's go. They said to compare experiment 1 and 2 and 1 and 3. So let's compare experiment 1 and 3. So what changed? So we have the same concentration working with, same temperature working with, but guess what? The form of zinc is different. In experiment 1, we have granules. Experiment 3, we have powder. So experiment 1, the zinc is granules. And in experiment 3, the zinc is powdered. So what happened with the volume? Experiment 1, we have 89, and experiment 3, we have 187. 89 cm cube, 187 cm cube. So we're seeing an increase in the amount of gas in the volume of gas liberated. So therefore the rate of reaction must have increased, right? So we're seeing an increase in the rate of reaction. But why is this so? So what happens when you change the zinc from granules to powder? There's an increase in surface area of the zinc. So increase in surface area results in an increase in rate of reaction. But why is this so? So the reaction occurs. Reactions, they occur at the surface of the particles. So when you decrease the particle size, so we're going from granules to powder, we're decreasing the particle size. We're decreasing the particle size, increasing surface area. So when you decrease the particle size, there's more surface area for collision to take place. Hence, the rate of reaction will increase. Right? So when we increase the surface area, increase surface area leads to a decrease, which is a decrease in the particle size. I think I should have said that the other way around. When you decrease the particle size, let's go again. When you decrease the particle size, you increase surface area. And this leads to an increase in exposed surface for collision, which leads to an increase in rate of reaction. Okay, so that's how you answer that. So the final one is experiment 1 and experiment 4. And what's the difference between experiment 1 and experiment 4? Experiment 1, you have the same, I hope you're following, the same concentration for the hydrochloric acid. You have the same form of zinc, but you have different temperature. The temperature is 30 for experiment 1, the temperature is 20 for experiment 4. So experiment 1, you have temperature being 30 degrees Celsius, and you have 89 centimeter cube of gas liberated. And for experiment 4, the temperature is 20 degrees Celsius, and you have 46 cm cube of gas liberated. Now, you're seeing a decrease here, right? So when you decrease, when temperature, so initial statement would be a decrease in temperature will result in a decrease in rate of reaction, right? But why is this so? That's what I'm going to ask. Why is this so? So what happens is that when there's a decrease in temperature, this results in a decrease in the kinetic energy of the particles. We all know about kinetic energy. So in a decreased temperature, there's a decrease in the kinetic energy. Decrease in the kinetic energy of the particles. Decrease in temperature leads to a decrease in kinetic energy of the particles. And then this would lead to a decrease in the frequency and the energy of the collision. So not only the frequency of the collision will decrease, but the energy in which they collide, by which they collide, would decrease also. So a decrease in temperature leads to a decrease in the kinetic energy of the particles and a decrease in the frequency and energy of collisions. and the energy of the collision is what is required to break apart the bonds of the reactant to give you the product. So you have a decrease in temperature leads to a decrease in the kinetic energy of the particles, and this will lead to a decrease in the frequency and energy of the collision, which leads back to a decrease in the rate of reaction. I hope we all see that and can appreciate that. So that was the final question. And as you can see, we run through and it was fairly simple. Some of them required some thinking through, but yes, so that's the final questions. So again, I hope that you did learn today in My Chemistry Hub. Join us again next time for our next video.